Yeah, good morning to the lecture Global Economics, and we are just within, so to speak, our technical part that later on we want then discuss quantitatively the dependence between unemployment and economic growth. And for this we have discussed, oops, where we are, the so-called Okun's law. And if we then had a look at this theoretical model, then we can translate this into gy equals a. This would be then the Okun parameter, delta u plus gy star, and this would be then also a parameter. And in the end, we end up, if we would identify gy, how did I do it in the right way, that I do not translate it in another one? No, it's okay. Here we have it. That we call then gy, we interpret as the dependent variable. Unemployment, change in unemployment as the independent variable, and a, just be a, the parameter which can be interpreted as the strength between these two variables y and x, so that if unemployment changes by 1%, then by 8 times x we obtain the change in economic growth, and gy star, the economic growth rate of potential output, is then the cut of the vertical axis of a model which represents just a linear line. And in order to estimate the dependence between these variables quantitatively, we have talked about this concept of linear regression. And here I gave you just an example where we said that the sales volume of a company depends on the visits of the persons who work for the company which they make. And then, where did I have this picture? Here it is. And then if we plot our data, y versus x, or here sales versus visits, then we said we want to find a linear line which fits these data points, and the condition which line we would interpret as the best line. This line should just minimize all squared distances with respect to our optimal line. Well, and then I yeah, just gave you some motivation why it is, where did I had it here? Why it is a good choice to use this condition of sum of squared distances to be minimized, because we could also think about other reasonable conditions. But that one condition is if we take only the absolute value of the distance, this that we get rid of this minus sign, that we um, choose a condition which yeah does not have this problem that negative and positive distances are just canceling out while summing up. This is, I think, quite clear, but then also a good reason to use since we want to optimize something, not using the absolute distance is that just in the minimum, and in this point we are interested when we are optimizing, that this function of an absolute value is not differentiable, and then we cannot use our standard condition, just taking the first derivative and setting this to 0. And then a much more deeper reason for this is that we find this squared distance in the normal distribution, which we find in many, many cases in nature, in social science, and also, you know, the central limit theorem, that if you increase the number of your data set, that then the distribution of the average value of your data set will go into the neighborhood of a distribution which is approximately the normal distribution. So this is the, so to speak, strength of this central limit theorem. That if you have a data set and you know nothing about the distribution of this data set, that then you can say, if I increase the number, so if I increase the number which I ask, do you want to buy this product? If you increase the number, that then the distribution of the average value of your data set will be then approximately normally distributed. And since we find in the description of the normal distribution here the squared distance, then this is also a reasonable choice to use the minimum of the squared distances. And the last one, I think you haven't heard already about this, is that this little guy, Carl Friedrich Gauss, 250 years ago, almost everything what we are doing in mathematics, he has already thought about it, that he found that the squared distance is also in deep dependence to the so-called maximum likelihood estimator. And actually he developed this procedure, and maybe also this is maybe quite interesting, he developed this procedure because his king he was in Brunswick, later on then in Hanover. He wanted to know how large is his country, and also our part here belonged to this country. And then he sent his most clever guy, Carl Friedrich Gauss, into his country, and he said, well, please measure the distances, that I really know how long are the distances in my country. 800, around 820, 830, something around this. Pardon? 1800. In 250 years ago it was. And well, then of course he sent one guy to some tower, for example, the tower of the castle in Jever and the windmill in Farel. I don't know if you have already seen this. These were 2 points. And then he had two guys and they looked at each other and then they measured these distances. And then they took another point that they had a triangle and they measured also the distances. Well, and of course, if you are measuring these distances, then you have an error that if you look at your data, that you do that the 3 points do not really fit into a perfect triangle. You have a slight error. Looking at this direction, looking in this direction, and looking in this direction. You write out, you are writing down your distances, and then you see, okay, I know that it is a perfect triangle, but your data doesn't fit for a perfect triangle. And for this, how do I correct my data? For this, he developed this procedure of minimizing the error. What would be then the best fitting line? And for this, he developed this procedure of minimizing the squared distances. Maybe this is also quite interesting. Where does it come from? And yeah, okay. So then we said, okay, this is our task. In the end, we have just a function depending on these two parameters, the cut of the vertical axis A and the slope B. Then taking the derivatives with respect to A and B, we obtain two linear formulas within with these two variables A and B, and so we have two equations, two variables, and then we know that if the determinant is is not zero, that this system of two equations is solvable. Well, and in the end, the outcome looks quite complicated, but it's just a formula for A and B. And then applying these formula, then we can calculate using this formula just the best line with respect to the condition of the minimum of the squared distances. And then we took our example and then we said, then we found that we have a slope of roughly 2 and a vertical cut of the y-axis of almost 4, and we ended up then with this fitted line. And the last aspect then was why did our manager ask for this? Well, the starting question was just, where did I have it? Here, that we want to know, well, should I hire a new person? Because I want to forecast how much would my sales volume increase if I increase the number of visits to 30. And I think then here, yeah, then with these linear regression, we find that we obtain a forecast for 30 visits of a sales volume of 63 euros. So maybe we can also plug in this in our picture. For this, let's copy these numbers here. And then we take 30 visits and our 63. And this would mean then let's take this in red as our forecast. No, all are red. Only want this one to be red. Now it works. Okay. And let's put this then here. And this would be then. These are visits. And this is sales volume. And this would be then our forecast for 30 visits. Okay, well, but with this, we are not done because, well, taking this, it is hopefully clear that I can do this regression for every data set. No matter if this fitting line is for us, by looking at it only by eye, a good line, a good fit or not. So let's think about data with this, which is distributed like this. Then, well, how would look like a good fitting line? Well, it could be this, it could be this. So we want now to have some number which we can interpret as, how good is our fit? And of course, we would say our fit is better if all data points are quite in the neighborhood of our linear line as we have it in our example. And for this, we want now to go on with the so-called correlation analysis. So in principle, we can do a linear regression for all data sets. But we want to know how meaningful is our calculation. Can I really rely on my forecast that if I increase my visits to 30, that then in the end I obtain a sales volume of around 60 or a little bit more? And this is then the correlation analysis, where we obtain a variable which we can interpret as a measurement for the strength of our dependence. And this was done by two guys, Bravais and Pearson, I think around 1900. This was done by them. And this correlation coefficient, maybe you have heard already in school about this number. This in general can lie between -1 and 1, where -1 we can interpret that we have a negative slope of our line and all data points of our data set are lying exactly on this linear line. So we have 100% fit, but with a negative slope, and the other way around, we obtain a +1 if we have an increasing dependence, and also on this increasing linear line, all data points are lying on this linear line. And for this, we use also the already seen concept, I think, by calculating it. Here we had already this number here. COV means covariance, which was defined as the product of the two distances, now without a square and without an absolute volume, and divided by n. And here we have it again. And actually, if we use an estimator, then we are not dividing it for an estimation by n, but by n minus 1. And just to briefly motivate it, well, of course, we are doing estimations, so we don't know in the end the true value. And then also 100 years ago was developed the concept what would be a good estimator and what are conditions to have a good estimator. And one condition is then that I want to calculate the estimator in such a way that the expected value of my estimator matches the true value. And this means that taking the expecting value, that my estimator is not biased. And then, this we won't do here in our short introduction in estimation. There, from a theoretical point of view, you can show that then you have to to divide your number not by n, what you naturally would do if you average something, that you just divide it by the number of your data set. But then you would obtain an biased estimator, a slightly biased estimator, and if you divided it by n minus 1, then you could you can theoretically show that it is not biased. So this is not dividing by n means that the estimator is not biased. And this would mean that the expected value of your estimator, and this HUT means is an estimator equals the true covariance. Okay. And here, of course, then we also see that this covariance can be positive and negative. And as I already mentioned it, if in general we have a dependence looking just on your data and your cloud of points has an increasing feature, then in general this would mean that an increase of x implies in general an increase of y, and this would then in the end mean that from your data set you obtain a positive number for covariance, and the other way, if the cloud is downsloping, then you obtain a negative value. But of course, here you have one problem. Think of you taking a data set with where you have some dependence on time. Something I don't know of what can you use depending on time. Or no, we are in economics, so not depending on time. Let's take on prices and in money. It's depending on the price measured in money. Then of course you can measure the price in euro. You can measure it in Turkish lira, which has an amount roughly, I think, times 100 or something like this, or some other currency. And this then, of course, would mean that this number would increase or decrease just because of the scaling. And therefore, the value, you can interpret the sign of this covariance, but the number itself, if it's 100 or 1,000 or zero point 0.3, you can hardly interpret because it depends just on your unit which you are using. If you are measuring, for example, prices in euro, British pound, or another currency, then just this number is changing. But we want to obtain in the end a number where we can interpret also the value of our number. And for this, yeah, we have to normalize this value. Maybe you have done this in your introductory courses also when you have calculated the mean of your distribution. Or compare and the standard deviation. Think again of the currencies. Then, of course, the mean, if you have an exchange rate of 1 to 100, then, of course, your mean would increase by roughly 100 when you are changing to the other currency, and also your standard deviation. And because of this, you want to interpret the standard deviation as a dispersion number of your data. Then you maybe have calculated the number where you divided the standard deviation by your average value. Because then, of course, take again your currency example. Both numbers are scaling with 100. Then the 100 just cancels out. And then you can really interpret this number, standard deviation divided by your average, by your mean. Then you can compare different data sets with each other. And the same we are doing with our covariance, and this would mean that we just divide our covariance in the by the square root of both variances of our two variables. Yes, of course, but yeah, but you can show that these horrible formulas, you can just see that this is the variance of x and this is the variance of y, and that you in the end have just have this number here. And this is then called the correlation coefficient. And here we also can show that this depends also directly to the slope of the linear regression. This was our slope of linear regression, y equals a plus bx. And what you then also do is that you are squaring this number, and this we call then the coefficient of determination. And this, of course, oh, here a square is missing. And then we have r square is element only within 0 and 1, not from -1 to +1. If we square it, then of course this number is then only within 0 and 1. And this number we can quite good interpret. In a minute I will show you also a further interpretation of this r squared, that we then can say, okay, if this number is 0, and for this let's go back into the definition of the covariance here. If this summing up would be the 0, this would then mean that there are quite a lot data points where the distances just cancel each other out. And I think you can think about this, that if this happens, then you do not find really a good linear line within your cloud of data points. And this then would mean, and in general, you can say if you have a coefficient of determination just around 0 or a little bit larger, that then you say, well, you have almost no dependence. But also you have always doing statistics, you have to be careful. What is your data about and what is your general question you are interested in? So we cannot say that in general an r square of 0.15 is showing no dependence. Maybe you are looking only for a very, very small effect. And this would mean that due to your question you are posing, what you want to find in your data, that you are very happy seeing just an r squared of 0.15. But on the other way, well, in general, you are looking for dependencies where you can say, okay, my data points are really in the neighborhood of this linear line, and this then would mean you look um, for data sets where you find an R squared which is in the neighborhood then of 1. And but where you then can interpret this an R squared of 0.9, 0.95, well, I can really rely on this dependence. But as I said, it really depends what you are asking for. Yep. Yeah. Well, this is then another question. Well, you have sometimes you have countries which fix their currency, especially on the US dollar. In Argentina right now, you have, due to the economic policy of the new president there, he said, well, I see that my own currency really, or the my people do not really rely anymore on my own, on the own currency in the country. They are paying only with US dollars. We had this effect also in the former Yugoslavia when all the countries were splitting from Yugoslavia. Nowadays, Serbia, Bosnia and Herzegovina, and so on. There was a time where you had a parallel currency that all the people were already, although it was not the official currency in the country, everybody was paying already with the euro because they didn't rely anymore on their own currencies. And then quite often the governments then start to couple their currencies directly onto the parallel currency, the euro or the US dollar. And then, yeah, you have this one-to-one matching between the home currency and the currency where you are fixing on. And then you, of course, would find an R squared between these two currencies, which is in the neighborhood of 1 or almost 1, of course. Yeah. So for this, yeah, if you are later on doing the linear regression for your country, and then maybe looking just at the two parameters, especially at the slope, and you say, well, it is in the neighborhood of 2. I'm really happy because I found almost the same as Mr. Okun 50 years ago. And if you then have a second look and you find, okay, my parameter is where I, so to speak, want to have it, but I then see I have only an R squared of 0.1, then unfortunately this would mean that your, so to speak, nice finding is not a good finding because the correlation coefficient or the coefficient of determination shows, well, you can calculate this data, but it has almost no meaning. Okay, and to talk a little bit more about this, let's start again with some data sets. Where do you think would be your r squared if you, or your r if you are looking at this data set here. What would you think? No, not a formula right now, but just using what I said about the correlation coefficient. These are the numbers, um, and if you just think fitting this data set, so to speak, by eye, what would you think? What could be this R? So more in the neighborhood of 1 or 0, yeah? Mm, mm, yeah? Yeah, almost 1, maybe something like plus 0.9 or something like this. Yeah, yeah. In the neighborhood, yeah. Okay. So let's then estimate plus roughly plus 0.9. Maybe our line would look like this. Actually, it is the same example as we have done it before. Then it would be 1, yeah. Yeah, it's plus. Yes, it's plus and by I. Actually, it is maybe also this is a good reason to use this squared, this minimizing the sum of squared distances. If we just fit by I for us a good line, then it is always very, very in the neighborhood of what where the line would ends up when you are using this minimizing method of square distances. So maybe also because you find this normal distribution in nature and we are living just in the nature. So and here the second one. So this is 2. So yeah, okay. I also think that somehow maybe it's a minus, yeah. But do you really think that here your R would be in the neighborhood of -1? 0.9. If you look again, the distances are quite larger here. So here we would say, well, this line fits quite well. But here, okay, I can do it. But is it really meaningful? So I don't know. Let's say I haven't it 0.5. Let's think of this. We will see it. These are the data. These are the data sets for this, and we will see it in a minute. And then the two last ones. 3. Yeah, and yeah, this is or this is 1. Yeah, plus 1. 0. Yes, great. Because it's totally symmetric. And this would mean this would fit it, this would fit it, and this also. All these, and then I do not find any dependence or any reasonable dependence, and therefore definitely here I would obtain a 0. Yeah, 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 yeah. Well, we will see it in a minute. We will calculate this, but I also want to show the r squared, that this we also can nicely interpret well, we lose this information of plus and minus, but in the end, we obtain always this information by just looking at our data set. And why we much more often use the R squared and not the R is this graphical interpretation that, so to speak, we can interpret R squared that it equals the proportion of variance explained by our model. Our model is y equals a plus bx. And again, think of this would be our data. Then, in order to aggregate your data, to describe your data, the first thing which we are doing is that we are calculating the average. So maybe the average here would be maybe this one. So roughly, yeah? Summing all this would be here y1, y2, y3, y4, and y5. And so y bar is then y1 plus y2, y3, y4 plus y5 divided by 5, just the arithmetic mean. So our average just represents our data set. We know our data are on average y bar. And now we take this model, and this model means, because this is just a horizontal line, and now we are turning this horizontal line a little bit upward. So here, not in red, sorry. Here, these are all our distances, and this we can, of course, then square, and then we obtain the variance of our data set with respect to y bar. So variance is calculated with respect to y bar. Yeah? You remember that the variance is then 1 over n sum yi minus y bar squared. And with a linear regression now, we are turning this horizontal line, and maybe in the end we end up with such a regression line. And this would mean that the distance of this data point y5 decreases. Here, we don't know. Maybe it decreases because now we are larger with our linear line. Here we have almost the same. Here we have a decrease, and here we have also a decrease. But in general, we can say now the summed squared with respect to the linear line is lower than our variance calculated with respect to the mean. So now the sum of the squared distances with respect to the linear line is smaller than sigma squared. And then, of course, we can say, well, the ratio of these two numbers, this we could then interpret as how good is our fit, or how much do we have improved by turning this linear line with respect to just taking the horizontal line, which means just calculating the dispersion with respect to the average. And for this, we can then surprisingly interpret r squared, that r squared just gives us this relative number. So, and this is then the next last slide, because, before we start then to calculate the correlation coefficient and coefficient of determination, that this r squared is that we can show that this, this was covariance of x, y divided by variance of x, variance of y, and this we have then also to squared, that this number is equal, this we can formally show, that this number is equal to y hat are the theoretical values lying on our linear line, theoretical values lying on the regression line. And now taking these values, not the data points, but the corresponding points lying on the linear line. We have done it, I think, in the other example here. These were the orange data points here. So using these, and maybe then y bar would be lying somewhere here. And now using these theoretical points, calculating the squared distances of these theoretical points with respect to our average value, and dividing this to the total variance. This is equal to our definition of the coefficient of determination, and this then means by turning our linear line, decreasing, so to speak, the distances, that then we can interpret this. If this number is 0.72, then we can say, okay, our model now that I take this increasing linear line and not the horizontal means that I can, so to speak, interpret this increasing line, that this explains 72% of the dependence between the two variables. Remember, not all data points are lying on this linear line, but they are now more in the neighborhood relative to the horizontal line. And if this coefficient of determination is, for example, 0.72, then this I can interpret as my model explains 72% of the dependence. And if it's 1, all data points are lying on the linear line, then of course I can say I have a one-to-one match. I can explain 100% of these dependence. Okay, some minutes left. And for this, then we want to calculate the coefficient of determination. Let's take again the same data set as before. And this we want to do again in Excel. Copy. Oops. The correlation analysis, and now this one we don't need anymore. And this also not. These two we still need. And now we need again our theoretical values lying on. This I have to recalculate. So here you see I just used the formulas within Excel to calculate our two parameters, and now again calculating the numbers lying on the linear fitted line means that it is A plus B times the X value, and using this equation here in order to calculate the coefficient of determination. Then I need the squared distance of our data point on the regression line with respect to the average of y and the squared distances of the data points with respect to the average of y. So I need also the averages here. Sorry, not x, but this one. And for this also we have a formula. This is called in German then Mittelwert, or in English it's mean if you have the English version. And for this then let's feed in the data. Oops. And then here y hat minus y bar. So this would be here y bar and y minus y bar. And both squared. So, of course, then opening the bracket, y hat minus y bar, the 27 again with the $2 we have to fix, and squared, and now y, oops, sorry, equals y minus y bar squared, and here I need $2. Copying this downward, and we need the sums of these two equals sum of these and also sum of these, and then we obtain r squared as just 482 divided by 572. This is just this formula here. So we obtain 482 divided by 572. Here I did something else. Let's do this again. Oops. This one. And also again the data points lying on this accent title y and x. So, and surprisingly, also in your software package, of course, you have directly a formula, and in German it is called Bestimmtheitsmaß, coefficient of determination. And again, you see here, feed in the y values and the x values, and hopefully we obtain the same. One trick question in the end. If I would calculate this the other way around, so reading at first the x values and then the y values. What would I obtain if I press now enter? Which number? I just interchanged x and y. Negative. It's r squared. It is still positive. Yeah, it is always positive. And can you say me which number it will? Oh, if you look at, hopefully it doesn't. If you look, this is one possibility to define it, or this is also, or and if you interchange within this formula x and y, what happened? Nothing. Nothing is changing because also covariance is not depending on if I put this bracket as the first or the second, it doesn't matter. So for the covariance, you can just say, well, it doesn't matter reading into the formula at first x or y. Yeah, sorry. Okay, then I think, yeah, I can put this, all this in. This doesn't work. So it works. And also the sums down here. And then we obtain 482.72 divided by 570 is roughly 0.844. What would be then r? Of course, the square root, and we know also the sign, since we know that this is a positive dependence. Yeah. So r is then just the root of our coefficient of determination, 0.9899. So plus square root of r squared is, since we have a positive dependence, and this is 0.99. So our model explains 84% of the dependence between sales and sales Y and visits X. Well, and this is what I meant here. Although I formulated almost no, low dependence, medium, high, almost full dependence, it's in the end then your decision or what you interpret as meaningful. Because now, after doing all our calculation, now we have the dependence that we found a parameter, a slope of 2. So increasing the number of visits by 1 means 2 additional euros. And we obtained that our model explains 84%. And if this is good enough for you, that you maybe before doing all the calculation, then you have to make at first the decision, well, if the outcome is a coefficient of determination of at least 0.6, so 60%, then I will rely on this forecast. Then it's okay for you. But if your manager, you as a manager have at first, well, I will only hire a new person, no matter what slope I have. I will only a person if my model explains more than 90%, and nobody can say to you, is 0.6 a good choice for you or is 0.9 a good choice for you? This decision you have to make. And if you said, well, for me 60% is enough and the outcome is 84, then you can say, well, this is okay. And then I can rely on my forecast that an increase of one visit would give me approximately 2 more euros. Yeah, because sometimes in statistics or if people are doing statistics, then they say, well, I always take the numbers which other people has taken before. So a confidence level, this is then another concept, confidence intervals. A confidence level of 90% is good for me because all other guys have said this. But this is not what statistic is about. It's a statistic means that it is an instrument to help you to make good decisions. So quite much things in statistics were developed in so-called decision theory in the beginning of the 20th century. And yeah. Okay, I think we had also to resolve our starting puzzle here. So this is, I think, our data which we, or 812, no, it's other data. Let's take this one and calculate the R squared. So 1, 2, 3, 4, 5, 6, 7. 1, this plus 1. 7, and we have 8, 12, 15, 16. 8, 12, 15, 16, 21, 22. 21, 22, but we are starting at 2. So this was example 1, and then let's take example 2, and there we have 24, 9, 18, 24, 9, 18, 8, 19, 8, 8, 19, 8, and then let's calculate R squared is coefficient of determination and we had also to calculate the correlation coefficient, which is the square root of this, and this for the other example. And here we have to be careful since we know it is a negative dependence. It's a falling line. We have to insert here a minus. So we end up with 0.98, even more. And here is minus 4.66. Quite good. So let's take this also here. Okay, so then we are done for today, and then tomorrow I take Germany, and we will do the regression with the real economic data for Germany. Thank you very much for today.